solving linear inequalities, this is very similar to solving an equation, but we're solving an inequality. So what we're looking for is multiple x values to make a statement true. So what we might have is, as a possible answer, is like x is greater than 2. So in an equation, we have x is equal to 2, meaning when x is equal to 2, we get a true statement in an equation. Well, in an inequality, it could be multiple x values that can make a statement true. So if we're looking at the inequality of x is greater than 2, we want all the x values that are greater than 2. So it could be any single number that is strictly greater than 2. So 2.001, 2.1, 2.2, 3, 5, 7, 100, 1,000. Any number greater than 2 could make this inequality true. So we can look at this a couple different ways, saying that x is greater than 2. If we have 2 on a number line, we want all the values greater than 2, so we don't want to include 2, and then we would want to highlight out to the right, so because we want all the values greater than 2. So our solution set would be going out that way as an interval. So this would be the graph. As an interval, we would write this as parentheses 2 going out towards infinity. And the reason we use parentheses is because we're talking about strictly greater than. If we're saying strictly less than or strictly greater than, we want to use parentheses as our endpoints of that value. But if we're saying less than or equal to or greater than or equal to, you'd want to use brackets as the endpoint of our value. Because when we use parentheses here, so when I'm saying parentheses 2 out towards infinity, that means I'm getting as close as I possibly can get to 2, but not include 2. So I'm saying 2.000000001, 2.0, 1,000 million zeros, whatever, 1, not including 2. So it could be very, very close to 2, but never including 2. Where if I said this, if I said bracket 2 out to infinity, that means I'd be including 2. So 2.0 would be a solution in that inequality. But for the example I wrote up, x is greater than 2, that would be all the values strictly greater than 2. All the values strictly greater than 2. Number 1, graph x is greater than or equal to 2, then write the solutions in interval notation. So graphing that x is greater than or equal to 2, we would just create a number line. And we'd want to say x is greater than or equal to 2. So I typically like to, there's a couple different ways that you could do this. Like some people might use like a filled in circle representing that we want to include that point because it says greater than or equal to 2. And then we want to highlight out to the right. I also encourage my students to do this. Like whenever they're doing inequalities, I like to get in the habit of doing this on your graph, on your number line. If it says x is greater than or equal to 2, we want to include 2. So I just like to throw a bracket onto my graph. That way I can see like, oh yeah, I'm including 2 because it says greater than or equal to. Then I want all the values greater than that. So I'm going to highlight out to the right. So this is our graph. And then in interval notation, that would be brackets 2, because we want to include 2, and we are going out to infinity. Number 2, x plus 3 is less than or equal to negative 5. On these inequalities, it's just like solving an equation. So you want to take this inequality, and you want to just get x by itself. And the same rules apply as you would just solving an equation. So you want to subtract 3 from both sides. That leaves you with x is less than or equal to negative 8, because negative 5 minus 3 is negative 8. So then our inequality is x is less than or equal to negative 8. So we'd want to identify our solution by graphing. So I'm going to create a number line. And I want to include negative 8 because it says less than or equal to. And then I want all the values out to the left, highlighting out to the left, and I want to include negative 8. So then I'm going to highlight out to the left. So x is less than or equal to negative 8, highlighting out to the left, because it's all the values less than or equal to negative 8, negative 10, negative 11, negative 15, negative 20. That's our graph. As an interval, we would have parentheses, negative infinity, up to 8 with a bracket. Whenever you have infinity present, you just use parentheses. You can never put a bracket around infinity because you can't stop infinity. So infinity goes on forever, so you have to use a parentheses. Parentheses just represents that this is going to go on forever. So like on number 1, I use parentheses with the infinity because I'm going out towards positive infinity, never stopping. But here, I'm coming from negative infinity. So I'm reading this as, as like a sentence, left to right. I'm coming from negative infinity. Out here is negative infinity, and I'm going up to negative 8, so then I stop at negative 8. So then our interval notation is left to right, negative infinity to 8. Number 3, solving negative 3x is less than negative 9. So this is just solving for x, same way you would with an equation. But when you divide for x, when you divide by negative 3, trying to get that x by itself, look what happens. I'm dividing by negative 3, so I get x. One rule that you want to know here is since we are dividing by a negative, since I'm moving a negative across that inequality, since I'm dividing by a negative, I want to flip that inequality. So that's less than is now going to become greater than. Negative 9 divided by negative 3 is positive 3. The reason I'm flipping is not because of this negative 9. It's because of this negative 3. So I'm dividing by negative 3, so I have to flip the inequality because of this. If I'm moving the negative, if I'm trying to divide or multiply across an inequality, I need to flip the inequality. So there's our inequality. Now we're going to go ahead and graph. X is greater than 3. And it's strictly greater than 3. So I want to not include 3. And I could represent that with a parentheses. And I'm going to highlight out to the right because I want all the values greater than 3. So I'm going to highlight out to the right. That's our graph. Let's write this into interval notation. So I'm starting at 3, reading it like a sentence, like left to right. You're looking at the number line going left to right. I'm not including 3. So parentheses 3. And the reason I'm not including it is because it's strictly greater than, not equal to. So 3 is 3 going out to positive infinity. Number 4, 4x is greater than or equal to negative 12. So I have 4x greater than or equal to negative 12. I am going to divide by 4. And I created this example for a reason. I wanted to illustrate the point of when we flip and when we don't. Here I divided by 4. So I get 1x. Here I have negative 12 divided by 4. That's a negative divided by a positive, but I divided by the positive, so I don't have to flip the sign there. I'm just going to leave it alone as is. Negative 12 divided by 4 is negative 3. So x is greater than or equal to negative 3. So I draw my number line. It's negative 3. And I want all the values greater than or equal to that, so I'm going to highlight out to the right. All the values greater than. And then write it into intervals. So that's our graph, write it in an interval. This time we're going to use a bracket, negative 3, and go out to the right. So I'm going out towards infinity. Next one, a little bit of a tricky solve here. 5 minus 4y is greater than or equal to 1. I'm going to subtract 5 from both sides. Get negative 4y. And I'm subtracting 5. I don't care about the inequality here. We only flip when it's a division or a multiplication of a negative. So I'm going to leave it as negative 4y greater than or equal to. 1 minus 5 is negative 4. Divide by a negative 4. So since we are dividing by a negative, we have to flip that inequality now. So this is going to become less than or equal to negative 4 divided by negative 4 is positive 1. So here's our graph. And I'm getting a little close to the camera there. 1 is here, and we want less than or equal to. So I'm going to use a bracket, and I want to highlight out to the left, right? Because we want to go y is less than or equal to 1. So I'm highlighting out to the left. And then as an interval, we are coming from negative infinity this time, and we're going up to 1 with a bracket. Some more examples, a little bit more complicated, a little bit more difficult. So let's take a look. We have 7a minus 4 is less than or equal to 3a plus 8. So we want to solve for a. We have a couple different options. Let's just get a on one side. I'm going to subtract 3a from here. 7a minus 3a is 4a minus 4 less than or equal to positive 8. I'm going to add 4 to both sides. Get 4a less than or equal to 8 plus 4 is 12. Divide by 4. not needing to flip. So a is less than or equal to 3. There's our line. So we have 3. We are including 3. And I'm going to represent it with brackets. And I'm highlighting out to the left because I want to include 3. There it is. As an interval notation, we would be coming from negative infinity. Bad negative infinity sign. Negative infinity up to 3 with a brackets, including 3 less than or equal to 3. Let's continue on. On this one, I want to distribute the 3. So I'm going to have 3x minus 6 less than or equal to 2x plus 4. A couple options. I'm going to subtract 2x. I'm just going to try to keep the x's positive. So I'm subtracting 2x. 3x minus 2x is x minus 6 less than or equal to 4. I'm going to add 6 to both sides. So we get x is less than or equal to 4 plus 6 is 10. Now, if you know how to solve equations, then solving inequalities shouldn't give you any really extra challenge. It's just making sure that you're careful with the division rules, like the division or multiplication of negative, and then making sure you know how to do the graph in the interval set part. So we have less than or equal to 10, so here's 10. I want to include 10, and I want all the values less than or equal to 10. So I'm going to highlight out to the left, because I want all the values less than or equal to 10. Interval notation coming from negative infinity again, up to 10 with a brackets. Last difficult example that I could find that I created here. So we're gonna distribute 2, distribute 3. So 2 times y is 2y. 2 times negative 3 is negative 6 minus 4 less than, or I'm sorry, greater than or equal to 3x plus 6 minus 17. Then I have combining like terms on this side. I also have combining like terms on that side. So I'm going to go ahead and combine those together. We have 2y minus 10 greater than or equal to 3x minus 11. Oh my goodness, we have 2 variables. I don't think that's supposed to be 2 variables. I'm just going to call that x. That's not supposed to be 2 variables. Mistyped. Now we just solve. I'm going to subtract. Let's subtract 2x because I want to talk about the sign here. So I'm going to subtract 2x. I get negative 10 greater than or equal to 3x minus 2x is 1x minus 11. And then I'm going to get x by itself by adding 11 to both sides. So we get negative 10 plus 11. That's going to be positive 1 greater than or equal to x. And the reason I did this, the reason I solved it like this, because I want to show you what happens in these types of scenarios. So the way you solve it, I get x on the right side. Now, what you have to do then is you have to either understand how to read that as like, which way am I going? Is it to the left, to the right? How does that look? Or just rewrite it so it's a little bit easier to read. So if I have 1 is greater than or equal to x, this can be rewritten as x is less than or equal to 1. I could just rewrite it with the x on the left side. Now, I'm not flipping the inequality. Don't think that I'm flipping it for the sake of flipping it. I'm flipping it because I'm just rewriting it. So I'm technically not even flipping the inequality. I'm just rewriting it. See how it is greater than or equal to with it pointing at the x? Well, when I rewrote it, it's x, and it's still pointing right at the x. It's not changing anything. It's still just pointing right at the x. The open side is facing towards the 1. Same thing here. Open side facing towards the 1. Nothing's changed. I just rewrote it. Now I'm able to identify x is less than or equal to 1. So I want all the x values less than or equal to 1. So here's 1. I want all the x values less than or equal to 1. So I'm going to highlight out to the left. And that's going to be negative infinity up to 1 with bracket. Next, I want to talk about solving compound inequalities, and then I'll have another compound inequality problem here. So let's do the compound inequalities. So compound inequalities are interesting because you have to work through it a little bit differently. So we have this compound inequality of 0 is less than or equal to 3x minus 2 is less than 6. So what we have to do is you can do this two different ways. You can branch this off into two different problems like this. So you could say, well, 0 is less than or equal to 3x minus 2, and 3x minus 2 is less than 6. You could branch it off into two different paths, which I'm going to do. I'm going to show you just branching it off into two different problems and then solving it and getting your answer. Some people also have the ability to solve these at the same time, like where you just leave it as is and then you add 2 to everything and then you offset. That's fine. No problems there. I just think that might get a little bit complicated and difficult if you don't have a strong understanding of what you're actually doing. Like until you develop that strong understanding, that's kind of hard to manage trying to solve everything at one time. But have at it if you want to. This is how I'm going to explain it. I'm going to just branch it off into two inequalities. So I'm going to take the blue brackets that I created and say 0 is less than or equal to 3x minus 2. And then I'm going to take the red brackets that I created and say 3x minus 2 is less than 6. So I'm just creating two inequalities here. And then we'll talk about the solution set when we get to that point. So let's solve both of them. So the first one, 0 less than or equal to 3x minus 2. I'm going to add 2 to both sides. 0 plus 2 is 2, less than or equal to 3x. Solve for x by dividing by 3. So I get 2/3 less than or equal to x. Remember what we just talked about? We talked about rewriting the inequality. So I'm going to rewrite this as x is greater than or equal to 2/3. The other inequality, 3x minus 2 is less than 6. Let's add 2 over. So we get 3x is less than 8. We're going to divide by 3. So we get x is less than 8 over 3. Two messy numbers, that's okay. It's not really a big deal at all. But you might need to convert to decimals if you don't know where they fall in the number line. Like if you don't know where 8/3 falls compared to 2/3, like what that looks like. So maybe you need to just get a quick decimal approximation. But it doesn't really matter if they're whole numbers or decimal values. Let's go to our number line. What we're looking for here is we're looking for the solution interval. Let's talk about these intervals first. So I have the first one, x is greater than or equal to 2/3. X is greater than or equal to 2/3. So we want all the values that are greater than or equal to 2/3. Okay. Now on the other inequality, we have x is less than 8/3. 8/3 would be almost 3, but not quite. So I'm going to put it over here. 8/3 is here. So for this interval, I want all the values less than 8/3. So I'm going to highlight out to the left. How do we identify our solution though? Because what we want is we want x values that are going to make this whole entire statement true. So we want x values that would make whatever I plug in for x right here, this 3x minus 2, whatever I plug in for x, I need to make sure it's greater than or equal to 0, whatever that result is, and it's also less than 6. So I don't want just any number, because if you look, the entire number line is highlighted right now. If I highlight out to the left, I'm going out towards negative infinity. Highlight out to the right, I'm going towards positive infinity. But that's not going to make both statements true. It's only going to make one of the two true. What we need is the overlapping ground between the solution regions. That is the only point that's going to make both statements true. It's going to make the 3x minus 2 greater than or equal to 0 statement true. It's going to make the 3x minus 2 less than 6 statement true. So we only want that overlapping ground. So that's my graph, the overlapping region here between this. Whoops, I knew that was going to happen. And then I want to write this into interval notation. So my interval starts at 2/3, and I'm using bracket there because it's greater than or equal to 2/3 right here. And I'm going towards 8/3. And I'm going to use a parentheses because I don't want to include 8/3 because it was strictly less than. So I'm going there. So that is my region. I'm not going towards infinity. I'm not going from negative infinity, anything like that. I'm locked between these two values right here because I need to make sure these x values are going to make the entire inequality true. Let's take a look at another one. So same exercise. We want to break this off into two. So we'll have 4 is less than or equal to 3x over 2 plus 5. And then we'll have 3x over 2 plus 5 is less than or equal to 6. I'll go through the solving a little bit quicker. We're going to subtract 5 for the first step here. 4 minus 5 is negative 1, less than or equal to 3x over 2. I'm going to multiply both sides by 2. I get negative 2 less than or equal to 3x. Divide by 3. Not flipping the inequality because it's the negatives on the left side there. I only divided by a positive. So I'm going to have negative 2/3 less than or equal to x. I'm going to rewrite this as x is greater than or equal to negative 2/3. So there's 1. So subtract 5 from over here. 3x over 2 less than or equal to 6 minus 5 is 1. Multiply both sides by 2. 3x less than or equal to 2. Going through the solving a little bit quicker, since I already solved a bunch of these already. And then we get x is less than or equal to 2/3. Okay. So we want x is greater than or equal to negative 2/3 and x is less than or equal to 2/3. And after you do this a lot, you will get very comfortable with understanding where that solution region is going to fall. But starting off, it's nothing wrong with just sketching it out. We have negative 2/3 and we want all the values greater than that. We have 2/3 and we want all the values less than that. So where is our solution region here? Where does the overlap occur? The overlap occurs right between the two values again. So we're going to have brackets, negative 2/3 going to 2/3 with a bracket. And they're both bracket because they both have less than or equal to as the inequality there. So good problems there. Last one. I have an application to all of this inequality. So we have a company is hosting a corporate dinner at a banquet hall. They have a budget for at most $3,000 for the event. The banquet hall charges $150 setup fee plus $45 a person. Find the greatest number of people that they can invite and stay within their budget. So this is a really cool example, especially if you're budgeting stuff and you have like a budget that you have to deal with where you don't want to go over a certain amount, but you have a lot of people coming to an event with some sort of fees. This is a really good example. So we want to set up an inequality. So we have $150 setup fee. So that's a flat charge. And then we're being charged $45 per person. So X can represent the amount of people. So if 2 people show up, 45 times 2 plus the $150 fee. 5 people show up, 45 times 5 plus the $150 fee. And what we want to do is we want to stay within this budget. And they have at most $3,000. So we cannot go over $3,000. We have to stay within the budget of $3,000. Now we just solve. Now it's a solving exercise just like how we've been doing throughout this whole video. So I'm going to subtract 150. 45x is less than or equal to 3,000 minus 150 divided by 45. So this was 2850. Then we want to divide by 45. X is less than or equal to 2850 divided by 45. This is an interesting answer because we get 63.3 repeating. You get a decimal value. So that now we have to really understand, well, how many people can we invite? I can't invite 0.3 repeating people. So I have to decide, am I inviting 63 or am I inviting 64? The answer being 63, because I don't want to go over. 64 people would put me over that budget. 63 people, I'd have a couple dollars left over, but we'll be good. We'll be good. We'll be within the budget with 63 people.